Welcome to the class on Applied Computer Vision and Image Processing. Today we will be discussing neural networks. The outline of the lecture is as follows. We will be discussing the limitation of algorithmic solutions or deterministic solutions. Next, we will discuss neurons and how they create networks in the brain. We will then speak about artificial neural networks, specifically perceptrons and three-layer neural networks. We will then speak about the training of neural networks. In the discussion of training, we will speak about the backpropagation algorithm, additional parameters that are useful to tune a neural network, and how do we define the topology of a neural network. Let's assume that we want to solve a hypothetical problem. So for instance, let's say we want to say which of these photos belong to the same person. Some of you may be familiar with these individuals, some of you may not know who they are. But suffice to say, you might be able to guess that this person and this person might be the same individuals. Right? And the hairstyle in this image, in the image over here, and probably this hairstyle is very similar to each other. Right? The hair is quite curly. Right? And the hair of this individual is also kind of similar to the hair of this person. But these two photographs do not match because the other features such as the nose, the eyes, and the lips are different between these two individuals. But if I asked you, how much is the difference? Can you quantify the similarity between the hair? How much is the curliness of the hair in this photograph? What is the curliness of this hair? How does it relate to the curliness of this particular photo? It would be quite difficult for you to estimate that. So there are a wide set of problems where human beings use approximate information to take a decision. These decisions are often based on parameters which cannot be quantified exactly using numbers. These are also based on combining multiple features together. So for instance, you would combine the hairstyle, the curliness of the hair, the shape of the nose, the color of the eyes, and the shape of the lips to decide which photographs belong to the same person. So you're combining different features together in different ways. So there are two aspects that human beings can very easily do. One, take a decision using approximate numbers without exact boundaries. Two, combine multiple features together and take a decision. And it's not just humans who are good at this. It has been shown that even animals like pigeons and mice can recognize objects. So for instance, to separate paintings of Chagall and Vincent van Gogh, pigeons could be trained to achieve almost 85% accuracy. Now the difference between these two paintings is quite vivid. So these paintings use dark colors and solid patterns, whereas these set of paintings are based on more textures and brighter colors. Now pigeons could be trained to identify and separate these two sets of images. Similarly, mice could be trained to run through mazes, and they could be trained to detect drugs. Now how can we do similar decision making in an algorithm or in a computer program? So today we will study how biological networks work and how you can design algorithms which can simulate biological networks and operate on combining multiple features together to take a decision. So how does the brain work? The brain is made up of a large number of neurons which are connected together to form a network. Each neuron is made up of a nucleus that is connected via an axon to a large number of synapses. These synapses attach themselves to dendrites, which are in turn connected to the nucleus. We are now going to handwave a little bit in order to understand how the nucleus works and how the network in the brain allows us to take decisions. More specifically, we are going to skip through some of the biological details. So the way the neuron works is current passes through the nucleus, down the axon, and onto the synapses. Once an electrical signal reaches the synapses, these synapses are connected to dendrites. Based on the distance between the synapses and the dendrites, so for instance, this is another nucleus which has a few dendrites emerging out of it. So there would be a certain distance between the synapses of this neuron and the dendrites of this neuron. Based on that distance and certain other properties of the fluid that surrounds the synapses and the dendrites, a portion of the charge passes from the synapses to the dendrites. So each synapse dendrite connection determines how much of the charge is passed along. So there might be a particular synapse dendrite connection where a significant amount of the charge is passed along. There might be a different connection between a synapse and a dendrite where very little charge is passed along. Now, all of these charges which reach the dendrite are accumulated at the nucleus. The nucleus applies a threshold on top of this signal and decides based on the input signals whether a current needs to be passed along the axon. That means, should the neuron fire, or should there be no current that is passed along the axon, in which case the neuron does not fire. So the firing of a neuron is based on two factors. One is, what is the amount of charge that is passed from synapses to the dendrites? And the second, after accumulating the charge that is obtained from all the dendrites, what is the threshold that the nucleus applies? And that will determine whether this axon will carry a current or not. So these two factors, the synapse and dendrite connection and the threshold on the nucleus, is what determines whether this axon is going to fire or is it not going to fire. Now, like we mentioned earlier, we are skipping over a few biological details. There is a lot more complexity to how the neuron fires. But in essence, these are the two major factors: the amount of charge transferred from synapses to dendrites and the threshold that is applied in the nucleus. This image shows a two-dimensional visualization of how synapses and dendrites could be connected to each other. So for instance, these synapses are connected to these dendrites. Some dendrites are at a significant distance from the synapses, whereas others are very closely connected. So this one, for example, is very closely connected. These dendrites are also very closely connected to these synapses. Similarly with these synapses. So the fundamental units which allow us to take decisions in the brain are neurons. The connections between synapses and dendrites and the threshold in the nucleus determines whether a specific neuron will fire or not. And all of these connections lead to a very complex network. For instance, the adult human brain consists of about 100 billion neurons and several trillion synaptic connections. And simulating all of this in a computer would require huge amounts of compute power. Biology has also shown us that it is not necessary to have a brain which is as complex as a human being in order to do useful tasks. So what do we mean by a useful task? So if you, for example, take ants. Ants, in comparison with human beings, have very few neurons. There are only about 10,000 neurons in an ant's brain. However, even with such a small brain, ants are able to do intelligent tasks. So for example, ants are able to form colonies. They are able to do collaborative activities like carrying food from one place to another. Now when you come to flies, the household fly, it has a little bit more complicated brain. The number of neurons in a fly is 10 times the number of neurons that an ant has. Now the fly can do even more complex activities. To just take a simple example, it's very easy to catch ants, but it's extremely difficult to catch a fly because the fly has compound eyes, it has nerves in the legs, it has vibrissae which are highly sensitive to the pressure of the air that surrounds the fly. So if you try to throw an object towards the fly, it's able to detect that an object is coming at it, recognize the object, and take evasive action. That kind of evasive action is not possible for an ant. Now imagine a drone or an airplane that has the same evasive capacity that a fly has. So a fly is able to do it with a biological network that has only about 100,000 neurons. Can we do the same activity using a similar network that is simulated in computers? Now, as you increase the complexity of the brain in biological networks, you see that there are increasingly more capabilities that are added on. So for instance, a frog can do continuous targeting. It can catch objects while it is moving through the air. So a frog can catch a fly while the frog is jumping. So the idea that computer researchers had was, can we simulate at least part of these biological networks and see if any useful tasks can be executed. So for instance, can we build a network containing 10,000 neurons, let's say, and simulate some properties of what an ant can perform? Can we generate a network that has 100,000 nodes and create a system that can have the same evasive action that a fly can have? I would strongly recommend you to go to this URL. This is a piece of software that can simulate worm brain. Researchers realized very early on the importance of not trying to simulate the entire human brain, but trying to see if a part of these biological networks can be simulated to solve any useful task. So for example, how can we solve a prediction task? How can we solve a machine learning problem? By building something that is similar to a biological neural network. Now we will introduce the concept of artificial neural networks, perceptrons, and three-layer neural networks. The perceptron forms the basic building block of an artificial neural network. The perceptron is made up of a bunch of inputs, including the bias, which are connected to an activation function through a set of weights. This activation function is connected to a squashing function, which keeps the output between a certain range, typically 0 to 1 or -1 to +1. Now the output of an activation function can be depicted in the following manner. The bias is connected to weight W0, input x1 is connected to weight W1, input x2 is connected to weight W2, x3 is connected to W3, and so on till xm connected to Wm. So the output of the activation function is a weighted sum of these inputs with the weights, and that turns out to be W0 plus x1 W1 plus x2 into W2 plus x3 into W3 and so on till xm into Wm. The squashing function performs an operation similar to applying a threshold on this weighted sum. So in effect, what the squashing function does is, if this weighted sum is greater than a certain threshold, then the output would be equal to 1. If this weighted sum is less than the threshold, then the output would be equal to 0 or -1. This entire result can be depicted or is very similar to the function y equal to f of wx plus b, where wx is representing this portion of the weighted sum, x1 w1 plus x2 w2 plus x3 w3, so on till xm wm, where m is the number of inputs, plus b represents the part of the bias, w0 would be equivalent to b. The function f would represent the squashing function. The squashing function we described is equivalent to applying a threshold on top of this weighted sum. Now we were doing a bit of hand waving when we said that. In reality, in most modern neural networks, the squashing function or the function f does act to keep the output limited between 0 to 1 and -1 to +1, but it does not apply an absolute threshold. You typically use a tanh, a sigmoid, or a ReLU function to ensure that the output stays between either 0 to 1 or -1 to +1. Some of you who are familiar with linear and logistic regression would appreciate that this equation is very similar to that of a linear or a logistic regression function. So the perceptron of a neural network is essentially implementing linear or logistic regression. We said that one of the activation function could be a threshold function, which can be defined like this: f of s equal to 0 if s is less than the threshold. That means the output of the network would be 0 if the weighted sum is less than the threshold, or it is equal to 1 if the weighted sum is greater than or equal to a threshold. The problem with using this as an activation function is that there is a sudden change in the output at a certain value of this weighted function. Now, this leads to difficulties when you train the system. This creates a discontinuity which cannot be differentiated and leads to a difficulty when you perform gradient descent. The squashing functions which are more popular in artificial neural networks are the sigmoid or the logistic function, which keeps the output value between 0 to 1. This red curve is the sigmoid function. The tanh function, which keeps the output value between -1 to +1, and the linear function. Now, all of these functions are differentiable, and this is their main advantage is in applying them in artificial neural networks. ReLU, or rectified linear function, is also a very popular activation function, especially in deep neural networks. ReLU operates like this: when the weighted sum is less than 0, ReLU stays flat, it stays 0. When the weighted sum is greater than 0, it's a linear function. This leads to efficient gradient propagation. There is no vanishing gradient problem or a exploding gradient problem in the case of ReLU. It's also computationally faster. In the case of the sigmoid or the tanh function, you need to compute an exponential value, this exponent, whereas no such computation is required in the case of ReLU. Let us now look at three-layer neural networks. Let us say that we have a data set made of these red dots and these orange color plus symbols. And this data set has two dimensions, dimension x1 and dimension x2. So there are two features, feature x1 and x2. For this data set, if you wanted to design a classifier, will a perceptron be able to separate these red samples from these orange samples? It's trivial to see that a straight line could separate these samples out, right? So the straight line can pass between these samples here. The perceptron would have this equation y equal to f of w1 x1 plus w2 x2 plus b, where this equation w1 x1 plus w2 x2 plus b would represent this line. This line can separate the red dots from the orange dots. And the squashing function f would ensure that everything above this line would have +1 and everything below this line would have the value -1. For example, if you take a point from here, for instance, if you took this point and substituted that in this equation, and if f is a tanh function, then because this point is above the line, the result in y would be a +1. In fact, if you submit even this point, for instance, the result would still be a +1. The result will be closer to 0 only if you're extremely close to the line. Even at a short distance away from the line, the value will become +1. Similarly, below the line, if you are very close to the line, the result y might be equal to or close to 0, but it would still be negative. The moment you get a little bit far away from the line, by nature of the tanh function, a little distance away from the line and the value will very quickly become negative or -1. So almost all the points which are orange in color and any point in this area, so whether you take a point here or you take this point or you take this point, the result for all of these points would be -1. Similarly, the value for all of these points would be +1. The result would be close to 0 only at points which are extremely close to the line. Instead of using tanh as the squashing function or the function f, if you use sigmoid as the function f, then all these orange points, when substituted in this equation, will give the result 0. And all these red points, when substituted into this equation, will give the value 1. In fact, any point above the line around here would result in the value 1 if this were a sigmoid. Therefore, the equation of a straight line in combination with the squashing function can perfectly separate this data out, because this data is linearly separable. So therefore, a perceptron can separate this data out, or a perceptron can be a good classifier for this data. However, what if your data was not linearly separable? What if your data was not distributed like this, but there was a different distribution? Will a perceptron still work? More specifically, what if your data was distributed like this? So here you have red samples enveloping the orange samples in more than one direction. In this case, a straight line can no longer separate the orange points from the red points. Therefore, a perceptron would not be able to fit to this data. we would need 2 lines minimum to separate these two classes. The process of combining two perceptrons and creating a single model can be done by using a network that has multiple layers, or more precisely, a 3-layer network. The 3 layers in this network would be the input layer, the hidden layer, and the output layer. There are different kinds of nomenclature that may be used for a 3-layer network. Some literature refers to this as a network containing 3 layers, the input, hidden, and output layer, and some literature calls this as a network with only one hidden layer. But both are equivalent and used interchangeably. It's more important for you to understand the internal working and appreciate how a 3-layer network can be used to model multiple perceptrons and combine the results and build a single classifier. In this example, we had discussed a data set that has two features, feature x1 and feature x2. But what if you had multiple features? What if you had features x1, x2, x3, and x4? Even that can be modeled using a neural network. So for example, here we have a neural network that has 4 inputs. Input 1, 2, 3, 4. The input layer, which is this layer here, these 4 nodes, does nothing but take the input values and passes them along to the hidden layer. So for instance, if you notice, the input number 1 is connected to hidden layer node number 1 and hidden layer node number 2. Input number 2 is connected to hidden layer node number 1 and hidden layer node number 2, and so on. This is ensured by the input layer. So the input layer does not do any processing by itself. The result of the hidden layer is represented using these two equations. In our example, the hidden layer has 2 nodes, node number 1 and node number 2. The result of node number 1 is h1 is equal to f, where f is the squashing function. It could be either logistic or the tanh function. F applied on I is equal to 1 to 4 xi wi1 plus w01. This value xi wi1 represents the weighted sum of all the inputs. So for instance, the first value would be x1 w11. That is input number 1 multiplied by the weight from input number 1 to the hidden node number 1. So that's x1 w11. The second value here when I is equal to 2 would be x2 w21. So that is input number 2 with the weight of input 2 to the hidden node, and so on for all the other inputs. W01 represents the bias that we discussed earlier. When we spoke earlier, every perceptron is supposed to have a bias which is set to 1, and then there is a weight associated with that bias. This bias is represented by the value W01. And f is your squashing function. Similarly, the output from node number 2 in the hidden layer is given by h2 is equal to f of I is equal to 1 to 4 xi wi2. So the subscript 2 refers to node number 2 in the hidden layer, plus w02. And w02 is the bias associated with node number 2 of the hidden layer. Now h1 and h2 are fed to the output node, which gives you this result. The final output y is computed as f of j equal to 1 to j equal to 2 h of I vi1, where vi1 is the weight from the hidden nodes to the output node. Now if you expand this, you would get h1 multiplied by v11, which is output of hidden node number 1. So this h1 multiplied by the weight v11 represents the weight from hidden layer number 1, hidden layer node number 1 to the output. Similarly, this for j equal to 2 you would have h2 v21 plus v0, which is the bias for the output node. Let us relate the hidden layer output and the output layer outputs to the problem that we discussed earlier. So let's say we had a dataset having these two features, and this dataset could not be separated by a single perceptron, and you needed two perceptrons. You could very easily train a neural network with 3 layers, where input layer would take the features x1 and x2 and pass it along to the hidden layer. In the hidden layer, you could have two nodes. Node number 1 computes the equation of this line, and node number 2 computes the equation of this line. This is very much possible because if you notice, the result of the hidden layer node is similar to the equation of a perceptron. And because the perceptron can represent a straight line, it's very much possible to have a hidden node with an equation that is trained to the parameters of this line. Similarly, you could have a second node which is trained to represent this line. So the parameters of the second node could be the parameters of this line. And the output layer would combine the results from these two lines together to generate a final result and ensure that all the samples within this region have a value of -1 and all the samples in this region have a value of +1, in case we are using a tanh function. If we are using a sigmoid as a squashing function, all the samples within these two lines, that is all the samples in this area, would have the value 0, and all the samples in this area, that is the area belonging to the red samples, would have a value of +1. We have looked at an example where two perceptrons could be merged to separate the data out. But what if your data was a bit more complicated? What if the data set was like this? You can see that there are two classes in this data set. There are two features, and each of these dots represents a sample. And you can clearly see by the colors that there are two classes here. Now the surface that is needed to separate this data is way more complicated than this surface. You probably need a surface which is like this. You can potentially model this kind of surface also with a neural network. All that you need to do in order to model complex or increased number of perceptrons is to add additional nodes in the hidden layer. Each node will represent a line, and even a complex surface like this can be represented by piecewise linear equations. Therefore, potentially any arbitrary surface can be represented by a 3-layer neural network, where the hidden layer has a large number of nodes. In the case of a 2-class problem, you would have only one node in the output. In the case of a multi-class problem, let's say a 3 or a 4-class problem, you would have 3 or 4 nodes in the output. If your attributes are only 2, that means if the input are only 2 attributes, you would have only 2 inputs. But if you have multiple inputs, then in the input layer also you can have multiple nodes. Thus, if you have a data set which contains multiple attributes, let's say your data set contains 50 features, then the number of nodes in the input layer will be equal to 50. If you feel that your data set requires a large number of surfaces to be effectively able to separate the two classes, then you need multiple nodes in the hidden layer. If your problem has two classes, then one output node is sufficient in the output layer. But if your problem has multiple classes, say your problem has 5 classes, then you would need 5 nodes in the output layer. So by changing the number of nodes in the input layer, hidden layer, and the output layer, any arbitrary problem can be modeled by using 3-layer neural networks. This slide just summarizes the result of a perceptron. So if you have 3 inputs and a single perceptron modeling these 3 inputs, then you'll have weights W1, W2, W3, and the result would be 1 divided by 1 plus e to the power of minus W0 plus W1 x1 W2 x2 plus W3 x3. Notice that we are using the sigmoid function here as a squashing function. By extension, if you have multiple layers, then each perceptron would have this equation, and the resulting perceptron, the final layer, would lead to this equation. So potentially an artificial neural network or a multi-layer perceptron is made up of multiple layers where you had one input layer and one output layer and potentially multiple hidden layers. Now, the result of such a multi-layer perceptron or such an artificial neural network with more than one hidden layer can be represented in the following way. The input layer, as we discussed earlier, does not do any processing. It just passes the data into the next first hidden layer. So layer 1 or the first hidden layer output would be h1 is equal to f1x. Now if we are using the sigmoid function, then that would be this function w1x plus b1, where w is a vector representing the weights of layer number 1 and h would be a vector of results coming from layer number 1 and passing it on to layer number 2. h2 would be a vector containing the results from layer number 2, and that is obtained by this function. Layer number 3 results would be obtained like this, and so on and so forth till you obtain the final layer results of the output layer. And by adding multiple layers, you can represent arbitrary complexities. But in general, even a single hidden layer is sufficient. Even a single hidden layer is sufficient to represent arbitrarily complex surfaces. You do not really require multiple hidden layers to represent arbitrary complexity. Now that we have understood perceptrons and three-layer neural networks, let us discuss how to train the neural network and identify the values of the weights. Let us say the problem that we want to work on is, given an input image, recognize whether there is an airplane in it or an automobile in it. In order to do this, we would need a large training dataset containing multiple images of airplanes and multiple images of automobiles. Recall that every node in the neural network is a perceptron, and the output of a perceptron is f of wx plus b, where f is the squashing function and wx computes the weighted sum of the inputs to that particular node. Therefore, the input to every node has to be a numeric value. Therefore, the input layer, when it passes on values to the hidden layer, it needs to pass on numeric values. Therefore, x1, x2, x3, x4 and so on, the input layer values should all be numeric. Now, given an image, we need to perform some feature extraction or feature engineering to convert the image into numbers that can be passed on to the input layer. After finishing the feature engineering, you need to decide how you will architect the network. In this process, you have to decide the number of nodes in every layer. In our example, we have two classes. So we are looking for two types of objects in each image. So the output label could be either a 0 or a 1. And this 0 or 1 depends on what kind of squashing function we are going to use in our output. We would use a 0 for one class label and a 1 for the other class label if we are using a sigmoid function. But if we would like to use a tanh function, then this has to be -1 and +1 respectively. The number of inputs would be equal to the number of features that are present. So the number of nodes that you'll have in the input layer would be 50 in this example because we have 50 features. Now let's get on to the hidden layer. The hidden layer has to take the input values, apply a weight, and then pass those values onto the output layer, which generates the final output. Typically, the hidden layer is kept at a value between the number of inputs and the number of outputs. In this example, let's say we've decided to use the value 16. In reality, you cannot arbitrarily decide this value. A network has to be trained multiple times, and you need to monitor the test and the validation error before you decide how many nodes would work for the hidden layer. So the number of nodes in the hidden layer is an empirical parameter that you have to decide based on trial and error. Now coming on to the output layer, in our example we have only two classes. and we are representing that with a 0 and a 1. So the output layer can actually just have one node. And when the node fires the value 0, or when the node outputs the value 0, we can assume that the class label is an airplane. And when the output node gives the value 1, we can assume that the class label is automobile. So now we have decided that the network architecture should contain 50 nodes at the input layer, 16 nodes in the hidden layer, and 1 node in the output layer. And we are using sigmoid for the output layer. Typically, in most neural network training packages, you can only set one activation function. So if you are using sigmoid for the output layer, you would be forced to use sigmoid for the hidden layer as well. But there are also several APIs where you can use different activation functions for different layers. So you could have sigmoid in the output layer and tanh in the hidden layer, or sigmoid in the hidden layer and tanh in the output layer. So once you decide this architecture, the number of input nodes, the number of hidden nodes, the number of output nodes, and the activation function to be used in each of these layers, you can then start training the neural network using this training data. Now, before we discuss the training algorithm proper, let's examine what would happen if the task on hand becomes a little bit more complicated. So for instance, let's say the goal of the network now is not to recognize 2 objects in an image, but to recognize 4 objects in an image. So for instance, the task now becomes, given an input image, determine if the input image contains an airplane, does it contain an automobile, does it contain a bird or a cat. Here, you may choose to say that, hey, 50 features were sufficient to differentiate between an airplane and an automobile, but now 50 features would not be sufficient. You may choose to say that we need 500 features. So your feature extraction or feature engineering might extract 500 values from every image. So your feature vector now becomes 500 features long. Therefore, the number of nodes in the input layer would become 500. Now let's move on to the output layer. You have 4 classes: airplane, automobile, bird, and cat. In order to handle 4 classes, you would need 4 output nodes, where each node outputs either a 0 value or a 1 value. And on top of that, you can also enforce the conditions that only one of these 4 nodes can be active at any given point of time. So that means only one of the 4 nodes must be giving a high value, all the others must have 0 values. Now moving on to the hidden layer, if you notice, the number of nodes in the input layer have increased, the number of nodes in the output layer also have increased. Evidently, the number of nodes in the hidden layer would also have to increase. So you set the number of nodes in the hidden layer to 120. Again, note that the number of nodes in the hidden layer would be something that you have to empirically adjust. So you begin the network by training it using 120 hidden nodes. But when training completes, you may decide that you want to train another network with, let's say, 150 nodes in the hidden layer and compare the performance of the 2 networks. So this parameter is typically something that is empirically adjusted. Training of the network is all about changing the weights of the hidden nodes and the nodes in the output layer by using backpropagation of error. To explain backpropagation of error in simple words, you can do it by initializing the network with random weights. So every node in the network and the weights in every node are initialized to random values. You take every sample in the training data and pass that sample through the hidden layer and then the output layer, and note what is the output obtained using these random weights. Obviously, the output will not be same as the true output that is required in the training data. For example, let's say you had this training data which contained 50 inputs and 1 output, and you wanted to train your network using this data. When you pass the first sample to it, the output that is expected is supposed to be 0. But because the network has been initialized with random weights, it's very unlikely that the output would be 0. If the output is indeed 0, then nothing has to be done. The weights don't have to be changed. You can assume that the weights were correct. But if the output is too high, that means instead of being 0, let's say the output was 0.8. Then you decrease the weights by a certain percentage of the error that is obtained here. at the output layer. For a different sample, it may so happen that the output is too low. For example, let's say sample number 2 has been input to the network. For sample number 2, the expected true value is 1. If the output that is obtained is also equal to 1, then nothing has to be done. But if the output is too low, that means instead of 1, if the output happened to be, let's say, 0.3, then the difference between the true value of the output and the value that is obtained is 0.7. So you would increase the weights of the output layer and the hidden layer by taking a percentage of the error. Now let's derive the equations that determine how much should the weights be changed based on the percentage of error. Let us make the following assumptions about the nomenclature that we are going to use in this derivation. The input node is assumed to contain I number of nodes going from 1 to I. The bias is represented by nodes 0 indicated here. The hidden layer has nodes going from 1 to j, and it also has its own bias. The number of inputs would be x1, x2, x3 and so on till I. So there are I number of inputs. The number of outputs would be 1 to k. So the output values would be O1 to OK. The weights that are used to generate the hidden layer output are indicated by Vij, and the weights that are used to generate the output from the output layer are indicated by Wjk, where I is an index into the input and j is an index for the specific hidden node. And here j is an index for the hidden node which is passing on its output to the output layer, and k is the specific output node. All the weights are initialized to positive and negative random values. In the forward phase, for every sample, the output is computed in the following manner. The output of each hidden node is computed like so. Hj is equal to f, which is the squashing function, summation I equal to 0 to I of xi Vij. We are summing from I equal to 0 because the 0th node or the 0th input represents the bias. This bias is always set to the value 1. So x0 will be 1. Similarly, h0 in this equation will also be 1. The output from each output node, where k goes from 1 to k, would be f of j equal to 0 to j hjwjk. The squashing function that we are using for this network is the logistic function. The derivation changes slightly when you use a different squashing function, but the broad steps would still remain the same in backpropagation. The error measure used to update the weights is obtained in this manner. It's essentially the sum of squared error, which is given as half of summation from every output node. You're taking the square of the true value expected at every output node minus the output obtained at that node from the neural network. And this error value is used to update the weights. A partial derivative of the error value is taken with respect to every weight factor, and that's used to update Wjk. Similarly, to update Vij, partial derivative of the error is taken with respect to Vij, and this is used to update Vij. So let's look at the output layer and figure out how to update the weights Wjk with respect to the error, which is defined like this. So let us say you have an input sample that you pass through the input layer, then the hidden layer, then you get an output value for that particular sample, and you compute the error. If you take a partial derivative of that error with respect to a particular weight Wjk, then the partial derivative would expand to give you this value. And this can be reduced to these values. True value of that particular sample minus the output value of that particular sample multiplied by output value of the sample and 1 minus output value of the sample. So this portion comes from here. Partial derivative of the error value with respect to OK. This part comes from partial derivative of OK with respect to OK hat. And Hj comes from partial derivative of OK hat with respect to the weight Wjk. From the previous slide, we know that the change in the weight is equal to the negative value of the partial derivative multiplied with the learning rate. And the weight is updated in this manner. And therefore, the final weight update is written in the following way. The weight Wjk at timestamp t, that means at iteration t, is given by the weight Wjk at timestamp t minus 1 plus learning rate times delta output k, which is defined like this, multiplied by Hj. The learning rate determines the amount of change in the weights. The learning rate is typically fixed as a value between 0.1 to 0.4, but in most modern neural network implementations, the learning rate is dynamic. It changes over a period of time as the network iterates over multiple samples. The typical approach is to set the learning rate to a high value initially when the network weights are all random. And as the network passes through several iterations of training, the weights would have stabilized a bit. After that, the learning rate is reduced. However, the learning rate and the specific values and how the learning rate is reduced is also an empirical process. Let's look at how the weights in the hidden layer are updated. The error rate is again defined like this. And you now take the partial derivative of the error with respect to a weight in the hidden node. So let's say Vij is one of the weights of a hidden node. And you're computing partial derivative of the error with respect to that particular weight. This resolves to partial derivative of the error rate with respect to Hj, partial derivative of Hj with respect to Hj hat, where Hj hat is defined like this, and partial derivative of Hj hat with respect to Vij. Partial derivative of Hj hat with respect to Vij gives xi, because in this summation you have many Vij's, and when you do a partial derivative of this with respect to Vij, you would get only xi. Partial derivative of Hj with respect to Hj hat gives this result. And partial derivative of the error with respect to Hj gives you this value. The partial derivative of the error with respect to Hj expands to partial derivative of the error with respect to OK, partial derivative of OK with respect to partial derivative of OK hat, and partial derivative of OK hat with respect to partial derivative of Hj. Now notice that there is a summation from k is equal to 1 to k in the error. Now due to that summation, this entire term resolves to this expression. Now to put everything together for the hidden layer, partial derivative of the error with respect to a specific weight in the hidden layer Vij evaluates to this, which in turn gives you this result. The weight update of a particular node or a particular weight Vij is given in the following way. Vij at iteration t, that means the new value of the weight, is equal to the old value of the weight. That means value of the weight at iteration t minus 1 minus the learning rate multiplied by the partial derivative of the error with respect to that weight. Now this evaluates to this value. Previous value of the weight plus learning rate multiplied by delta hidden j, which is defined like this, into xi. This slide shows a summary of all the steps involved in backpropagation. You first initialize all weights in the network to positive and negative random weights. The forward phase or computing of the output is done like this using these equations. The error for every input value is computed in the following way, where t is the true value which is expected at the output. This value t and the input values x are obtained from your training data. For instance, let us say this was your training data and you are inputting sample number 1. For sample number 1, the true value tk would be 0, and the value xi would be this vector 0.9360, 0.9274, and so on, all these 50 values. So x0 would be the bias, x1 would be 0.936, x2 would be 0.9274, and so on and so forth. Let us say instead of using this data set, which requires only one node in the output, you were to use this data set, which requires 4 nodes in the output. The value tk would change. The true value for sample number 1 would now be 1000, and the value k would range from 1 to 4. And the number of output nodes are 4 in this case. The number of inputs are also different. In this example, we had assumed that we will have 500 inputs. So x0 again in this equation would be the bias, but x1, x2, x3 would range from 1 to 500 values, and x1 for example would be 0.3374 and so on. Irrespective of whether the number of input nodes are 500 or the number of input nodes are 50 or the number of output nodes are 4 or 1, the derivation of backpropagation remains the same. The output value OK is obtained using these equations. Now, because the initial weights are all random, OK is not likely to be close to Tk. So there will be a difference between Tk minus OK. Using these error values, you update the weights. And the weight update is done using partial derivatives. So the weight of the hidden layer to the output layer, that is wjk, is given as the new value of wjk is equal to the old value of wjk minus learning rate multiplied by the partial derivative of the error with respect to wjk. Similarly, the weights which the hidden layer uses to generate its output, that is the weights Vij, are updated like this. The new value of Vij is equal to the old value of Vij minus learning rate times partial derivative of the error with respect to Vij. And the partial derivative of the error with respect to wjk is defined in the following way, and this is the result. The partial derivative of the error with respect to Vij is obtained like this. And the final result is this. This is how the weights are updated.